Welcome to the first video on binomial probability. In this video we're going to take you from algebra with which you're very familiar and end up working with probabilities, ultimately taking us from algebraic manipulations that you already know, and we're going to end with a lot of calculator computations through our Nspire CAS. So if you remember from class, there are four criteria that make something a binomial situation, and the first of those is that, well, it's binomial, so there have to be exactly two outcomes. Our first example is going to be flipping a coin. So with flipping a coin, there certainly are two outcomes, heads and tails. The outcomes have to be independent. So in this case, flipping a coin, one coin toss is certainly independent of another coin toss. A coin has no memory. There have to be fixed probabilities from one trial to the next. Well, certainly the probability of heads is 1/2 on each and every toss. Coin has no memory, those probabilities don't change. And there also have to be a fixed number of trials. And in this case, we are talking about specifically flipping a coin 2 times. So we are satisfying all of the criteria that we need for a binomial situation. I'd like to start off by just creating the sample space. So if I flip a coin 2 times, well, the first coin could be heads and the second one could be heads, or first heads then tails, could be tails heads, could be tails tails. So if I wanted to, I could say, let's look at, I could look at number of heads or number of tails. I'm just going to look at number of heads, and we're going to also look at the number of times that each one of those occurs. So if I flip twice, I could have anywhere from 0 to 2 heads, and 0 heads occurs down here exactly 1 time. 1 head occurred in both of the middle ones, so that one occurred twice, and 2 heads occurs up here, so that happened 1 time. If I wanted to, I could also change that. Instead of sort of a frequency count, I could instead look at a probability chart. So 0, 1, 2, and there were a total of 4 outcomes. So the probability of getting 0 heads was 1 out of 4, 1 was 2 out of 4, and twice could happen 1 out of 4 times. All right, so whereas this one is a frequency distribution, this one is a PDF. We are actually looking at the distribution of all probabilities, and this is a function because I can input 0, 1, or 2, and the output now becomes a probability. So this is the standard PDF that we've been looking at. All right, so what would happen if I flip a coin 3 times? What you see here is the entire sample space written out for what can happen when I flip 3 times. So let's recreate the same 2 charts that we had up above, looking at the number of heads, which if I'm flipping 3 times, I could have 0, 1, 2, or as many as 3 heads. And how many times does each of those occur? Well, 0 heads is down here at the bottom. There was 1 of those. Exactly 1 heads, so that could be this one, this one, this one, and all the rest have more than that. So there were 3 of those. 3 heads up here, that happens once, and the other 3 that remain uncircled or checked all have 2 heads in each one, so there's 3 opportunities for that. So there's my frequency chart. What about a PDF for this? So number of heads could be 0, 1, 2, or 3. And if I convert those frequencies into probabilities, there were a total of 8 different outcomes that could have happened. So 1 out of 8, 3 out of 8, 3 out of 8, 1 out of 8. And again, what I have is my PDF for flipping a coin 3 times. All right, let's recreate the exact same thing with flipping a coin 4 times. First thing is we want to see the sample space. So in the overall sample space, flipping a coin 2 times, there were 2 outcomes for each, 2 raised to the 4th because there were 4 trials. I know there's a total of 16. There's the full layout of all 16 potential outcomes. And let's recreate one more time a frequency chart showing us the number of heads versus the number of times that each one occurs. And because I'm flipping 4 times, I could have 0, 1, 2, 3, or 4 different outcomes. And for 0 heads, that's down here at the bottom, there's again one of those. There was exactly one outcome that had all 4 heads. And what about exactly 1 head? Scanning what I have, looks like I've got one of those here, and one here, and one here, and one here. So I see 1, 2, 3, 4 of those. And if you go back through, you can see that there will be 6 outcomes that have 2 heads and 4 outcomes that have 3 heads. And so if I wanted my PDF for the very same thing, number of heads is going to be 0, 1, 2, 3, or 4. And the probability of each one of those, since there were a total of 16 outcomes, this becomes 1 out of 16, 4 out of 16, 6 out of 16, 4 out of 16, and 1 out of 16 again. All right, so I can get PDFs. I can flip a coin any number of times that I want to. Very clearly, this is growing exponentially in terms of the number of different outcomes. So I'm wondering if there is a bigger pattern that we can use. So overall, let's look at like all 3 of our trials together: the flipping coin twice, 3 times, and 4 times. So when I flipped twice, the number of outcomes that I had, if you look back in the video, we had 1, 2, and 1 for 0 times, 1 result, 2 results. All right, so what would happen if I flipped my coin 3 times? Well, then I had 1 occurred 3 times, 2 occurred 3 times, and 3 occurred once. What would happen if I flipped my coin 4 times, the one we just completed? Well, I could have 1, I could have up to 4 different outcomes, and then it was 4, 6, 4, 1, which you might recognize as exactly the same thing as that Pascal's triangle that you had in the past. Maybe you wrote that a little bit differently, 1, 2, 1, 1, 3, 3, 1, so it's a little easier to see that the element in each, every element in each row is the sum of the 2 pieces above it with 1s on the ends. So from here, this is now outcomes of flipping a coin, outcomes of a binomial situation is exactly the same thing as what we were getting when we were expanding polynomials back in our algebra or pre-calculus classes. So how can I extend that idea into working, getting some of these results a lot faster? For that, we're going to turn to our CAS. So now I'm working in my Nspire CAS, and we saw some numbers showing up from flipping numbers of heads and tails that looked a whole lot like the coefficients from expanding binomials. And again, note binomials from algebra, binomial probabilities now in statistics, it's the same idea. The command that we're going to use a lot here is expand. And just to reconfirm what you had seen before in your algebra and pre-calculus classes, if I have a binomial x plus y and I square it, then I see those coefficients of 1, 2, and 1 that you had seen before. If I expand cubed, I see a 1, 3, 3, 1 as my coefficients. So I'm getting exactly the same thing that I had seen before, just now showing up with heads and tails. A beautiful thing about using the CAS is we don't have to restrict ourselves to just x's and y's. What if I actually name these variables to be what's happening within our probability? So let's expand heads plus tails. Those are my 2 separate outcomes in my binomial situation, and the exponent is the number of flips or the number of trials that I'm doing. So what I see now is 3 heads. The coefficient tells me how many times that could happen. 2 heads and a tail will happen 3 times. 1 head and 2 tails will happen 3 times. 3 tails will happen with its coefficient exactly once. So I can see with one really quick experiment how many different ways each outcome can happen. Reducing the size of the output just a bit, What would happen if I expanded flipping a coin 4 times? And now I can see my 4 heads occurs once, 3 heads and a tail occurs 4 times, 2 heads, 2 tails occurs 6 times. You see the entire probability. Now here's what's really nice. If instead of just expanding the probability to compute the number of times, what if I put in front of each one the probability that it happened? When I do an expansion of a binomial, any coefficients that the variables had also receive the same powers. So when I expand that, what I see, I have shifted from just the number of outcomes when I expand just the outcomes to now I'm actually seeing the entire PDF with a description of what each number represents. So this now tells me that 3 heads can occur with 0.125 probability. 2 heads and a tail occurs with a 0.375 probability. The really beautiful thing about the expansion is it automatically shows me each probability within the PDF along with a verbal description of what each one is. If I had done this not with decimals, but I had done this with the fractions, it's a little bit harder to read the probabilities, but I can actually get the exact results. So 3 heads occurs with the coefficient is 1/8. 2 heads and a tail occurs with 3/8, so they don't exactly stack up in the Nspire CAS printout, but you get exactly the same result. So knowing now that I can use my CAS and polynomials, let's flip back and solve a problem from our text. So on a quick read here, we've got some area where 8 out of 10 households are subscribing to cable TV. So what that tells me is the probability that someone has cable is going to be 0.8, and we got a pretty large area. And let's see, we're going to let X denote the number of 6 households. So I'm going to randomly sample 6 households and try to see how many of them actually have cable television. Well, what that tells me is I'm actually doing 6 trials. I've got probability of cable, and that also tells me that the probability of not cable is going to be 0.2. And so what I have here is another binomial probability. There are exactly 2 outcomes. One household's we're going to assume isn't going to be affecting another household's probabilities, fixed probabilities, fixed number of trials. We've got a binomial situation. So let's try to solve this using our Nspire. We're going to try to calculate the probability that 3 of our 6 households have cable television. So our situation was binomial, and we want to try to figure this out using polynomials. And the way we're going to make that happen through the expand command that we're used to. And our 2 outcomes are cable and not cable. And there were 6 household surveys, so we're going to raise this to the 6th power. And if I expand this right now, then what I see is that there was 1 household, like just through a random selection, there could be 1 household that had 1 experiment where all 6 houses had cable, 6 households where 5 had cable, 1 had not cable, 15 households where 4 had cable and 2 had not cable, and so on. And the polynomial is pretty long. I could hit the up arrow, and if I scroll to the right, then I can see all the rest of the polynomial and continue to scroll over. So it's just long, but I can get out all of the values that I needed to. Now, what if we played the exact same thing here? Now, it's trying to compute the probabilities. So instead of just having the variables, we're going to put in front of each one, 8 out of 10 households had cable, so 0.8 is the probability of that, and 0.2 is the probability of not having cable. And when I expand that, I now see all the probabilities for each situation within the sample space. We have everything. All right, what we were looking for here is household, what's the probability that 3 houses have cable? So that would be 5 houses right there. There's 4 houses. Let's go over and grab another term. And so now what I can see is from this term, it appears that 3 houses with cable, meaning 3 houses with not cable, occurs 0.08192 of the time, and that is the solution that we wanted for that problem. So our probability in this case, what is the probability that 3 houses have cable? That's the 0.08192. So what about the probability that all 6 houses have cable? Well, what's lovely is that is exactly the same situation, the exact same polynomial. I just need to pull off a different term. So flipping back over here, we wanted all 6 to have cable. So that's our very first term. And there we have this. Let's copy that one and move that over. So here we have 0.262 as the probability that all 6 have cable television. 0.082 is the probability that 3 of the houses have cable. All right. So what would happen if we tried something a little bit more complicated and said the probability that x was less than 5? So what I need to do now is find, well, x less than 5, that's the probability that none have, plus the probability that 1 has, all the way up to the probability that 5 have. And there are a couple different ways to figure out this probability. Let's jump over to our polynomial first and pull off this thing directly. So I'm looking for all of those probabilities except for the one where all 6 people had cable. So I'm going to start by going here, and I'm going to delete off the term where all 6 had cable, and what I really want is the sum of all the rest of those coefficients. And so one way that I can do this is hop all the way to the end of this line. I'm going to take advantage of the CAS. If I can make all those variables equal to 1, they'll just sort of go away. So I'm going to do a vertical line for under the condition. Let's let cable equal 1 and not cable equal 1. Just to make my variables go away, they'll all be raised to different powers, but I'm now going to be left with each coefficient times a bunch of 1s, and we'll add all those up. And what I get really quickly is that 0.737856, and that is the probability that I was looking for. Now, a slightly different way of playing the exact same problem is I could play complements. The probability that something was less than or equal to 5 is the complement of what if all of them actually had cable and I subtract that from 1. So I ought to be able to find this same answer by just subtracting a single probability instead of adding up all of the other different pieces. So flipping back over here to the CAS, I'm going to say 1 minus, go up and grab the probability that all 6 had cable, and I get exactly the same result. It doesn't matter which way I try to solve this. So be aware of complements, grabbing terms out of your individual polynomials. You have lots of different possibilities for how to solve this. Welcome to binomial probability.